Okay, so thanks for inviting me along to this very interesting session, and thanks for the three great speakers. So this talk will be a slightly different style of talk. I wanted to make this a sort of introductory one and also a fairly short one, which I guess probably works. I think maybe we're a little behind schedule. So I wanted to talk about a sort of dual method of representing conditional independent relations, namely supermodular functions, which are, if you like, dual to structural imsets. They've been mentioned a few times already, but I will remind people what they are and why they matter. Milan said in his talk that I would be discussing the connection of extreme supermodular functions and the facets of certain important polytopes. I could have done that, but I'm not actually going to do that. There's quite a lot to say about supermodular functions, and I just wanted to focus on the kind of basic facts of them. So what you're going to hear is pretty much the kind of highlights of various interesting connections that Milan and colleagues have uncovered about connection between structural imsets and supermodular functions. And then I'm going to be kind of speculating about what role these functions might play in further research on conditional independence relations. Okay, so I think it's worth just sort of stepping back a bit and thinking, what is it that we want from a conditional independence representation formalism? So throughout, I'm going to use the abbreviation CI to stand for conditional independence. So let's just plod through these bullet points. I think preferably it's good if all probabilistic conditional independence structures can be representable, and I think it's okay to just restrict ourselves to probabilistic ones. As Milan said in his initial introductory talk, one of the main motivations for creating the imsets in the first place was that the various graphical representations we have are not of that nature. For example, for DAGs, there are all sorts of conditional independence relations we can't represent with DAGs. That's why we have MAGs, for example, but graphs are not always the way to go. And second bullet point is, although maybe graphs aren't the be-all and end-all of representing conditional independence, there's a lot to be said for them. Not least their visual representation is very intuitive and helpful, particularly if we're interested in causality. So it's good to be able to translate to and from well-known graphical representations. So we've seen already these things called standard imsets, which is a translation from a DAG to a structural imset. That's the sort of thing we want more of, no matter what our choice is of representation formalism. Thirdly, how do we get to conditional independent structures representing things of interest? Typically, we don't construct them by hand. Typically, they're learned from data, so we want to have methods to enable us to estimate the true structure from data, which is usually called learning. Another desideratum is that preferably we'd like it to be easy to check whether some particular conditional independence relation holds. So if someone gives you a DAG, then you can use, for example, D-separation, or you can construct the minimal ancestral graph and moralize it and use either of those two methods to determine whether or not some particular conditional independence relation holds. And that's obviously an important thing to be able to do. And more generally, it's useful to know whether one conditional independence structure includes another, in the sense of having the same, at least all the conditional independence relationships of the first one. So these are things that we would like. Penultimately, it's useful to be able to produce marginal and/or conditional independent structures. So if we had, some way of representing the conditional independencies in some particular distribution, and then we wanted to consider some of the variables as latent, it'd be nice to easily construct a new representation for that latent model, preferably without too much effort. And lastly, thinking practically, we would like some sort of compact representation. So, for example, standard imsets are nice standard imsets of DAGs, I should say, because now we have lots of different sorts of standard imsets with MAGs and so on. But standard imsets for DAGs have a nice compact representation because the vector in question is very sparse. They're basically zeros. So I think these are the things that I no doubt there are other things, but I think these are some of the things that we want. So the question is, So what I'm going to be exploring is to what extent supermodular functions give us some of these nice things and which things they lack and so on. So we need to start with a basic fact, which is in Milan's 2005 book, which I encourage people to read. So let's just read it out here. Every conditional independence model induced by a probability measure with finite multi-information can be described both by a structural imset and by a supermodular function. So the point is that both representation methods are complete in this sense. Okay, so so that's one point to supermodular functions. So that's a good thing. So let's start with that. Now let's just remind people what a supermodular function is. I know Milan mentioned this in his original talk, but I think it's worth reminding people. So it's a function to the reals. Doesn't necessarily have to be an integer valued function, although often we restrict attention to integer valued functions. So for each subset of some ground set capital N there, we have a real number associated with that subset. And the supermodularity condition is the one given to you there by that inequality. Okay, so when we add A and B together to get the union, the value associated with that is bigger than the two individual subsets, even once we subtract off the intersection there. Okay, so that's supermodularity. So Milan, the quote I gave you from Milan in the previous slide said that you can represent every probabilistic conditional independent structure by a supermodular function. How does one do that? So if someone gives you a supermodular function M, and you want to know whether the conditional independence relation is A independent of B given C is represented by the model given by the M. That is the case if the dot scalar product of the supermodular function with the relevant elementary imset is 0. Okay, so I think this came up in, I think, Milan's talk at a certain point. So that's how you do it. Okay, so important point to raise here is that's a very simple thing to compute. Yeah, if you've got some reasonable representation of M, then computing that scalar product is pretty straightforward, and you just see whether it's 0 or not. Okay, so it's a bit simpler, I would argue, than with a structural imset, whereas what we have to do there is you have to subtract off the relevant elementary imset and check whether the thing you've got left is a structural imset, which is a bit less obvious, I would argue. So a bit of notation there. If we've got supermodular function little m, I'm going to represent the conditional independence model by script n superscript little m, and that's just all the conditional independence relations which hold in that model. Okay, so as is typically the case in this line of work, we view the model as a finite list of conditional independence statements. So that means that, if you like, big structures are those structures which have lots of conditional independence relations. Okay, so that you've got to be clear about that, because if you have lots of conditional independence relations, then the set of consistent probability distributions is of lower dimension than otherwise. So you've got to have an intuition about what bigness means here. So the conditional independent, the model where everything is independent of everything else, conditional on everything else, is the biggest possible one. So just kind of keep that in mind for slides that come later. So that's how a supermodular function represents a conditional independence model. I would argue that's a fairly straightforward one, a straightforward way of that happening. As has been stated earlier, supermodular function represents a conditional independence model. It produces a disjoint semi-graphoid. So if you check the semi-graphoid algorithms, you'll find that they will work, as they should do, of course. And let's talk a little bit about how one can get hold of a supermodular function. So in particular, if one has a probability distribution, as long as it's got finite multi-information, then you can very easily construct a supermodular function which gives you the conditional independence model for that probability distribution. How does one do that? You just set your supermodular function to be the multi-information function for that particular probability distribution. Okay, so what is multi-information? So if someone gives you a subset of your random variables, multi-information is nothing other than the relative entropy for that marginal relative to the product of the univariate marginals. So in a sense, it's a measure of the amount of dependence going on in that particular subset. So that's the multi-information function is a supermodular function, and moreover, it's one that gives you exactly the right model. Okay, so if someone gives you a distribution, then getting an appropriate supermodular function is extremely easy. Okay, let's carry on. So I'm just, if you like, plodding through interesting facts about supermodular functions. So we need to relate them to structural imsets. So what is the connection here? So if you give me a supermodular function M and a structural imset U, then one question of interest is the model defined by M, does it contain the model defined by U? That is the case if and only if the scalar product between those two vectors is 0. So you've got that you can view that as a sort of incidence relation. So in Milan's book, he uses Galois theory to explore that incidence relationship. So you get the two kind of meeting, if you like, if you get a 0 there. So that's an important connection with structural imsets. So you can see from this that the 0 vector, where there's a 0 for every component, for every subset, that is supermodular, also submodular. That represents the independent structure, okay, Tn, which is basically everything, all possible conditional independence relations, because obviously then you're going to get a 0 no matter which structural imset you plug into that dot product. So that's the most fundamental connection to structural imsets. So let's look a bit more into the kind of details, if you like, of supermodular functions. And at this point, we're going to look at the, if you like, analog of elementary imsets. So up till now, we haven't really been looking at supermodular functions. We've been focusing on imsets, and these elementary imsets, if you like, the building blocks from which more complex imsets like combinatorial ones or structural ones are built. So we have something similar with the supermodular functions, these things called skeletal. So a supermodular function M is skeletal, and as with all of this talk, all this terminology and theorems and so on come from Milan's work, mostly the book. So the term skeletal is defined there. It's a supermodular function is skeletal if there's no other supermodular function R such that R strictly contains M and R is a subset of the set of all possible conditional independence relationships. So they're basically these sub-maximal conditional independence models. So they contain very, very many conditional independence relations. So they're at the opposite end of the models from the elementary imsets, where you just have a single conditional independence relation. This is like everything but missing a few, if you like. So these are kind of important, and let's have a few facts about them. Milan proved that you get a supermodular function is skeletal. For it to be skeletal, it's got to be a non-zero function, and it's got to belong to an extreme ray of a cone of supermodular functions. So supermodular functions constitute a cone, so you can add them and get another supermodular function. You can multiply them by a positive scalar and get another supermodular function. Hence, they're a cone, and cones are a bit like polytopes, and the correspondence of a facet in the polytope is a ray in a cone. So these are the vectors, if you like, on the edge of the cone. So that's the nature of these skeletal ones. So just to give you an idea of how many there are, if you have 5 variables, then it was computed by Milan and colleagues that we have 117,978 skeletal imset supermodular functions if you normalize and integer value them. Okay, so we've got to do a bit of normalization for it to make sense to count them. And these broke down into 1,319 permutation types. So just for comparison, there are a mere 80 elementary imsets for 5 variables. So there are way more of these skeletal supermodular functions than there are elementary imsets. So I guess that's a downside, that we've got kind of bigger things to deal with the supermodular functions. A bit more about these skeletal supermodular functions. So evidently one thing we might wish to do is, if someone gives us a structural imset U, we might want to construct a supermodular function which represents the same model. So for example, someone gives me a DAG, and you create the standard imset, which is a structural imset, and you might say, well, maybe I want to do something with supermodular functions now. Give me the supermodular function which represents that model, in this case, a DAG model. How do we do that? Well, if someone gives you an imset U, we can view this as the intersection of a bunch of models, which give us we can view that as the intersection of a bunch of conditional independence models. So this will be a model. So we've got a bunch of models here, M superscript R, for various different little r's, and we're going to intersect them all together, and that will give us the same model, the model also defined by M. So what's the connection here? So we collect together all the skeletal imsets. So that's notation there with the diamond, means set of skeletal imsets. So we have the skeletal imsets. For each one of those, you can imagine we check whether the model given by the structural imset U is contained within that for MR, for that particular skeletal one. And if it is, we add it to our set script R. And remember that doing that check of set inclusion is nothing other than computing a scalar product and seeing whether it's 0 or not. So that's no big problem there. Once we've got all these skeletal imsets, we just add them together. That will give us another supermodular function. Typically, won't be typically an extreme supermodular function, but a supermodular function nonetheless. That's the supermodular function we want. Okay, so so the point here is that adding supermodular functions is like intersecting them, whereas in the case of structural imset, adding them is like unioning them. So we can go from a structural imset to the relevant supermodular function and get exactly the same model. One can also go in the other direction, but I decided not to go into that, partly because I was worried I might make a mistake in the explanation. Yeah, so that's how we can get from one representation to the other representation. So now we get to this slide here. So one of the reasons why I got interested in supermodular functions, apart from the reasons to do with the polytopes that Milan mentioned, is that I'm interested in being able to easily construct marginal and conditional dependence models. And one of the nice things about supermodular functions is that that's pretty straightforward. So this is from a paper called Basic Facts Concerning Supermodular Functions by Milan. And in a sense, it was always going to be easy, because you can think of supermodular functions as a sort of slight abstraction of the probability distribution itself, yeah, because it's basically because for a given probability distribution, you can construct a supermodular function by the multi-information function. So there's a very tight connection with probability functions. So basically, suppose you've got a set of variables M and a bigger set of variables N, and you can, if you subtract the difference between N and M is a couple of subsets, disjoint subsets D and E. So that means that N is partitioned between D, E, and M. Then you can do a projection, okay, to get rid of D and E or both of them. So there's a mapping there which will take you from a function from let's assume this is a supermodular function. We're interested in supermodular functions. So a supermodular function on N, the bigger one, to a supermodular function on M, using D and E, and it's called the projection, the minor projection, where you delete D and extract E. So you're getting from one function and generating another function. So this is a mapping from functions to functions. What is that mapping? It's pretty straightforward. If you've got in the smaller, if you've got S, which is a subset of the smaller collection, the smaller ground set M, what happens when you apply, you've got the original M, then you apply the mapping. So what value does you get for S? It's something we're going to call RS. It's nothing other than the M applied to S union E. So the kind of D things have disappeared. Okay, and we get this nice connection between conditional independence relationships holding. So in the mapping, so is A independent of B given C according to the model given by this mapping? It's the case if and only if A is independent of B given C and E in the original supermodular function. And this is for any elementary imset. And so basically this gives you an easy way of generating marginal models. All right, so so in the general case, we've got this set D and also this set E. But if we just make E the empty set, then this is straightforward marginalization. And if we make D the empty set, this is like conditioning on E. So it's kind of easy, if you like, to do this sort of thing. I think easier than with imsets. Maybe Milan can correct me if I'm mistaken about that. Maybe I missed some tricks with structural imsets and marginalizing them. Okay, so I just want to, as I said, this is just a kind of whistle-stop tour of interesting things, or things that I think are interesting about supermodular functions. There's very many other things that one could say about them. So looking ahead, one of the a nice connection which has already been exploited, most notably by Milan, is the connection with matroids. So if people know about matroids, then they will probably know that the rank function of a matroid is always a submodular function. It's not actually true that every submodular function is the rank function of some matroid, but many of them are. And as Milan mentioned at the beginning, supermodular functions are pretty much the same as submodular functions. It's not, they're just a mirror image of each other. Milan showed in a very useful paper that if R is the rank function of a connected matroid on some ground set C, then that function there you can see, which is just the cardinality of S intersected with the ground set minus the rank function, that is an extreme supermodular function. If the matroid was not connected, I haven't got time to go into what matroids are or what connected matroids are, but if it wasn't connected, then we would get a supermodular function which is not necessarily connected. The point I'm going to make here is, for those who know about matroids, or at least know what they are, one way of getting, sorry, let me put it this way, one way of defining a supermodular function, extreme or otherwise, can be via a matroid. If you give me a matroid that has a rank function, and from that, which is submodular, and from that submodular function, I can generate a supermodular function fairly straightforwardly, and that gives me a conditional independence model. So I think there's a lot more work to be done. Some work has already been done by people like Milan and also Matusz on the connection between matroids and the conditional independence structures which you get from the supermodular functions generated from the rank functions of these matroids. So I think that might be a very interesting direction to go in. The other thing I'd like to say is that we should exploit this easy marginalization and conditioning to get an analysis of, this might be useful for graphical models with latent and selection variables. Okay, something appeared, maybe that was something to tell me to be quiet, but I'll finish now, so that's okay. Thanks a lot.
Thanks very much, James. Does anyone have any questions for James? Just raise your hand if you do. So Milan, go ahead.
Maybe not just a comment or extension. Thank you, James, for making a nice overview about this research on supermodular functions. Let me just explain. I really tried at the beginning to use supermodular function to describe conditional independent structures in the way you described. But the problem was that really there is a big difference if you describe them in terms of structural imsets, where you have only 80 elementary imsets, yes, in case of 5 variables, but this huge number of 117,000 of skeletal imsets. So it's really one of the reasons why I propose more structural imset than supermodular function was this.
Okay.
But you are right that some of the operations for marginalization and conditioning are much more elegant in context of supermodular functions.
Mhm.
But there is some recent research. I hope that there is a chance to characterize well the criterion to this to characterize the extreme supermodular function in combinatorial terms.
Okay. No,
Okay.
So I actually had a question of my own, which was, so you talked about this method for going from a supermodular function to an imset, or maybe it was the other way around. How sort of computationally easy or hard is that operation in general?
Certainly, if one approaches it in a naive sense, it would be computationally hard because hopefully people can still see people can still see this.
Yeah.
So the kind of simplistic way is you plod through all your skeletal supermodular functions and compute this scalar product and see whether it's zero or not, and then add it to your sum, and then eventually, once you've gone through all of them, you've got yourself your function. The problem is exactly the one that Milan mentioned, is that there are too many of these skeletal functions. Yeah, so you just go through them one after the other, and checking whether whether mu is a subset of MR. That's going to be very laborious. So yes, it's, the question that is interesting, and I don't know the answer to it, is whether one can do this in a more efficient manner. So the thing that occurs to me is that what we're doing all the time here is that we're concerned with whether certain scalar products are zero or not. Okay, and the problem we have is that there's a very high dimensional space with these scalar products, and maybe if we do it in a direct manner, it's going to take forever. But this is exactly the problem that kernels were invented to do in machine learning. Yeah, so the idea is that at the end of the day, we do this thing where we project things to a high dimensional space, and then we take a dot product. Maybe we just go straight to the function. So I mean, this is just pure speculation on my part, but maybe something based on kernels might get us around the problems that a naive method would give us.
Yeah, it's a very interesting idea.
If I may comment also, one of possible advantages of the supermodular approach is that we have a very natural way how to estimate it, the structure from data, and it's simply like compute the multi-information function or estimate of it. Yes.
Yeah.
So that will be more straightforward approach into learning.
Yeah, but we've got to be careful there. That will just give you, so if you take your data and compute the multi-information values for the empirical distribution, then all you've got is you just got something which just reflects the empirical data. What we usually want is, we don't want the empirical distribution, we want the true distribution from which that data was sampled. So I guess we'd have to do some sort of rounding or something. I don't know.
Yeah. You are right. Yeah.
Okay, well, thanks very much, James. And let's thank all four of our speakers for really interesting talks. And I'd like to also thank the organizers for allowing us to have this session, and to all of you for attending and listening. Thanks very much.
Thanks for organizing it, Robin. Thanks to the organizers for having us.
Yeah, thanks, Robin.
Thank you for everyone. And today's share is ending.
Thanks. Bye.
Bye.
Bye, everyone.